Hello again. Gonna do some more modern algebra. I'm Scott Hader, and here we go. This time we're going to be talking about cosets and Lagrange's theorem. This lecture might run a little bit long. I'm not sure. It might be about 30 minutes or so. So you might want to divide it into 2 periods if you're going to watch it. Just a little advice. It can be a little bit heavy. So there's a lot in here, and I condensed it a lot, and I tried to make it as simple as possible. I hope you like it. So let's just get started. So first thing, cosets, to start out with, they're subsets of the group, and they partition the group. So when we say partition, we mean divide it into equal groups, equal sections of equal size. So I'll mention a lot of this stuff over and over again. I think it's pretty easy. It's just a matter of keeping everything straight. So when we talk about Z12, we know that's 0 through 11, and one of the subgroups is the subgroup generated by 4, 0, 4, and 8. And if we add 1 to each element in that subgroup, we get 1, 5, and 9. We add 2 and 3, respectively, we get 2, 6, and 10, and 3, 7, 11. If we add those numbers to each of our elements, right? So these are cosets, and well, let me finish the slide here. So these are all cosets, and they partition Z12. See how we've divided Z12 up into 4 cosets. So each one of these, they're not groups. If my mouse would work. These are not groups individually. This is a group. It's a subgroup of Z12, but these individually are not groups, but they're cosets. They partition Z12. Alright, so let's continue. Little note on left and right cosets. So this is just the way they talk about left cosets and right cosets. When they say left cosets, all they're talking about is the number that you add on the left, or the number that when you're talking about generic algebraic terms, it's the element that you're multiplying by the set by on the left. When they talk about right cosets, they're talking about the number you add on the right, or as we'll see in a little while, the element that you multiply by on the right. So it's really not that confusing, but you just need to see the rest of the lecture to understand what I'm saying. So I'm just going to try to say it several times, so hopefully by the end you have some grasp of it. So a couple details here. The number of left cosets always equals the number of right cosets. However, left cosets do not always equal the right cosets. So keep those 2 facts in mind when you're working problems. Okay, so one of the problems we have here, find all the cosets of the subgroup 4z of z. So I think we've done something similar to this in the past. 4z is the multiples of 4, the integers z, and when we multiply all of those by 4. So here's the integers, and if we add 0 to each of those, we get this. If we add 1, we get this, 2, and 3. And notice these 4 sets here partition this set. Together all of these make up the set of integers. So they partition the integers. Notice again, we're not saying subgroups, they're cosets. So we partition the integers. We found all the cosets, which are sets. Okay, let's continue. Find the index of the subgroup generated by 3 in Z24. First we got to know what the index is. The index is simply the number of cosets it takes to partition the group. That's all it is. the number of cosets we end up with to partition it. And we're going to call it R. And you'll get used to this. I'm just throwing this here. We're not going to use it in this example probably, but in a couple more slides we're going to be using this letter R a little bit to represent the index. So now, the subgroup generated by 3 is this set here. Subgroup generated by 3 plus 1 is this group here. And the final set, did I say group? I meant set. And so the final set is here. And that together, this makes up our entire set of Z24. So how many sets did we need? We needed 3. So the index is 3. That's all it is. 3 cosets, the index is 3. It's easy. Easy, easy. Okay, continue. Lagrange's theorem. Here we go. So, it's a very popular theorem, and let's see what it is. Basically, all it says is the order of a group divided by the order of one of its subgroups is a whole number. In other words, the order of the subgroup divides the order of the group. So if the order of the group is 12, then the order of one of its subgroups has to be something that goes into 12. 1, 2, 3, 4, 6, or 12. So, another way we can write this is the order of the group, which we write like this, which we've seen before. That's not new. And the order of the subgroup, which we use H for the subgroup. And like I said earlier, we're going to use R for the index, which once more is just the number of cosets it takes to partition the group. And one note here is that this only applies to finite groups. So Lagrange's theorem we can only use for finite groups. So we will use that fact later on. A lot of details. A lot of details in this class, a lot of details in this lecture. So I just put this formula here just for your reference so you can look up at it if you need to. And so let's say we have the group Z24. Now the order of the group is 24, isn't it? Now let's say we take a subgroup generated by 3. Well, what's the order of that group? It's 8 if you count them all up. 0, 3, 6, all the way to 21, there's 8 elements there. And we could find the number of cosets it would take to partition Z24 by doing the order of the group divided by the order of the subgroup, which is 3. So we could have done this earlier too. We could have used this formula. Remember we wrote out bracket 3 plus 1, bracket 3 plus 2, and bracket 3 plus 0. And that partitioned the group. We could have done this as well. So I hope it makes sense. I don't expect you to, have it all memorized and mastered at this point, but I think that for the most part it's pretty intuitive. So I hope it's kind of starting to come together a little bit. So what's really helpful for that is to do some true or false questions. So for our first true or false question, every subgroup of every group has left cosets. That's true. Why is it true? Okay, let's look at finite groups. For finite groups, we can use Lagrange's theorem. Remember, we just said that. And we know if we have a subgroup, well, for finite groups, we're going to get some number R, which is a whole number, which represents the number of cosets. So it's definitely going to have left cosets, since that R is going to be a whole number. By the way, this isn't a formal proof. This is just an explanation. And for infinite groups only have one structure. They all look like this structure. The same structure as the integers. And the integer only has subgroups as multiples of the integers. So for instance, 4 times the integers, which we did earlier, that's a subgroup of the integers. And just like we did earlier, we found that you need 4 cosets to partition the integers. So it's always going to be the number of cosets, it's always going to be n. So it's always going to have left cosets. Number 2. The number of left cosets of a subgroup of a finite group divides the order of the group, of the whole group. Well, what do you think? I know it's probably too many words right now. But let's break this down. We're talking about a finite group. So what can we use? I hope you said Lagrange's theorem, or you were thinking it. In that case, you'd be correct. If you multiply our formula by the order of h and divide by r, you get this, right? And definitely the number of cosets, the number of left cosets, divides the order of g, right? Because the order of h is going to be a whole number. So that's true. Okay, I'm just trying to think about what you guys are thinking about right now. Whether you're just staring at it blankly or kind of like, okay, yeah, I hope it's making sense. I don't want to jam too much information, too many words into the lecture, so I'm not going to over-explain. But so next we got a subgroup of a group is itself a left coset, and I'll just give you a hint. It's true. The reason is why. Well, I'm giving you a hint on the explanation. I already gave you the answer, but just look at this. This is a subgroup, isn't it? This is a subgroup, and this is the left coset, and these are the same, aren't they? So, ta-da! Last one. Only subgroups of finite groups can have left cosets. Only subgroups of finite groups can have left cosets. So, I'm not going to tell you the answer to this one, but I'll give you a hint. The answer is somewhere in this lecture. So if you want to look back, there's not too much. It's your choice. But you can figure this one out on your own. Okay. So here we go. Every group of prime order is abelian. And I don't expect you to know whether this is true or false or not. You might have a good guess though. If you guessed that it was true, you'd be correct. And I'm gonna sort of do a proof here. It's a I can't remember how formal it is. I think it's pretty formal actually. So let's talk about it. So every group of prime order is abelian. So if you remember from part 3, we talked about cyclic groups. And we have a proof in that lecture that all cyclic groups are abelian. So if I can prove that all groups of prime order are cyclic groups, and I know all cyclic groups are abelian, then I know every group of prime order is abelian. So I'm not going to prove part 3, but I'm going to prove that every group of prime order is cyclic. So let's set it up. Let G be a group, prime order P, and to prove it's cyclic, we need a generator that generates the whole group. So I'm going to call that element, some element A. This is going to be our generator. And we're going to let it be a non-identity element. So it's any group, any element that's not the identity. And that element generates a subgroup, right? For sure it generates a subgroup. And just trust me on that, or you can review lecture 3 on cyclic subgroups to get a better understanding. So let's call that subgroup that it generates H. It's nothing new. We'll use H for subgroups. Now, notice the order of G is P. That's what we said, and we said the group is of prime order, P. So order of group is P. Now, we're talking about a finite group, aren't we? Because it's of prime order. So, what can we use? Again, I hope you said Lagrange's theorem. So, by the way, I missed on my test one little detail I didn't put. There's state Lagrange's theorem, and I forgot to put finite groups on there for finite groups only. And so I got points off, so got a little chip on my shoulder. But I don't want you to miss the same points. So just remember that. Lagrange's theorem only for finite groups. Alright, so here's Lagrange's theorem. The order of our group is P. The order of our subgroup is the order of the subgroup generated by A. So I'm just subbing in that subgroup there. And that's going to be some whole number. So the only way this can be a whole number is if this right here is 1 or it's P. Those are the only things that divide a prime. So we know it's not 1. Otherwise it would be the identity. The subgroup generated by the identity is just the identity. You take the identity times the identity times the identity times the identity. You keep getting the identity. All it generates is the identity. So we know that it has to be P, since it can't be 1. And if it's P, if the order of our subgroup is P, then it's the same size as our group, which means it's our group. Thus, A generates G. Therefore, all groups of prime order are cyclic. And using our lecture 3, all cyclic groups are abelian. Yeah, that's right. No, all groups of prime order are abelian. Pulling from all of it now. So that was a true or false question. Okay, so this is the last thing we got today, is a proof. This is going quicker than I thought, actually. No, one more thing before the final proof, just to give you a little background. A couple details. So cosets don't actually look like this. You know, like we showed some examples. You know, you can generate the subgroup generated by 3, you just add 1 to it, you know, you add 2 to it, add 3 to it, add 0 to it, you get the you know, Z24, the whole group. You can partition the group that way. But they don't actually look like this. When we do proofs and things like that, they look like this. Here's our subgroup, right? This is the subgroup generated by 3. Here's our subgroup, H. Here is our element not in the subgroup it's just in the generic, it's just in the group. And we're doing some binary operation with H. It doesn't have to be addition. So you don't have to 1,000,000% understand that. You just have to be willing to kind of go with it for right now. And I think it'll make sense later on. It will definitely make more sense the more you spend time on this stuff. So here's a few details. Capital letter. See, why did I use a lowercase and an uppercase letter here? Well, I use uppercase because that means it's the whole set. It's every element in that set. We take A and we do some fixed element A. Mouse, I'm warning you. We take this fixed element A and we do some binary operation with each element in the set to come up with the set. Because after all, cosets are a set. They are sets. And we use lowercase to mean a specific element, a fixed element. So they are sets, not necessarily groups. Now if we had a 0 plus bracket 3, that would just be bracket 3. which is, well, that would be a subgroup, wouldn't it? But that's the exception. Cosets are not necessarily groups. So since they're sets, a lot of our problems we use set theory. So I hope you remember some set theory. If you don't, well, you better remember. And I hope that my explanations are good enough. If you've done it at some point, I think it will come back. So this is the last thing we got today. It's a proof. It's going faster than I thought. So let H be a subgroup of a group G, and it gives us the information that G inverse HG is in H for all G and G, and for all H and H. So these are elements in the group, and these are elements in the subgroup. And when you can say multiply. By multiply, I mean do the binary operation between them. It's telling us that this is an H. And it wants us to show that every left coset is the same as every right coset. Remember, the left coset, we take the element that's in the group and we multiply it by every element in the subgroup. So to show that they're the same, that means they're equal, doesn't it? And how do we show that something's equal in set theory? We have to show that they're subsets of one another, don't we? So, part 1, we're going to show that GH is a subset of HG. So, what do? We take an element in GH, and we're going to take this element. We know that this is in H. And this is our fixed element G. So this is in GH. And since this is an element in H, and so we multiply them together, and what we get when we multiply them together, we get HG. So this is going to be in big HG, isn't it? So we just showed that if we take an element in GH, which is this, we get an element in HG, which is this. Now we need to show that if we take an element in HG, we get an element in GH. So this time, we're going to take the same element. We need an element in H. So this element's in H. What we can do is we can do a little manipulation. We can plug in G inverse for G here. So instead of writing G inverse, we're going to plug in G inverse to that. So we'd write G inverse to the inverse. H, and then remember we plug in G inverse for G. And then we multiply all that times G. And that's in HG. And when we multiply all that out, we get GH, I'm sorry. So we've just shown that if we take an element in HG, that we get an element in GH. So we've shown that HG is a subset of GH. Since we've shown that they're both subsets of one another, they're both equal. And that's the end of the proof. And that's the end of today. Thank you for watching. Leave me some feedback. I haven't gotten a lot of feedback, but what I have gotten has been really positive. So I do appreciate that. And really, I just hope you guys have a better understanding of this class and I hope you can see that it's really cool material, and I hope you can find some enjoyment out of it. So that's all for today. See you next time.